Hi everyone, let me welcome you to the 13th session of ECT 204 Signals and Systems. Today we discuss the orthogonality of signals. This video is organized into your learning outcomes, orthogonality of continuous time signals, and then the orthogonality of discrete time signals, and then we discuss orthonormal signals, and then the summary of understanding. So in this video, you will understand the orthogonality of continuous time and discrete time signals. Then you will understand the meaning of orthogonality, how it is useful in communication receivers, etc. Then you will learn about orthonormal signals. Signals are usually represented as vectors. So the orthogonality of vectors is applicable to signals as well. Two vectors are orthogonal if their dot product is 0. That is, if they are at 90 degree apart, their dot product is 0, we say the vectors are orthogonal. So likewise, signals can be represented as vectors. So if two signals are represented, x1 and x2 are orthogonal, then that dot product should be 0. And this dot product is realized as this integral, that is integral from minus infinity to infinity x1t x2t dt equal to 0. This integral minus infinity to infinity x1t x2t dt is actually the dot product between the signal x1t and x2t. So if this dot product equal to 0, then the signals are orthogonal. Now let us think about a simple case. Let us consider two signals, that is x1t is a cos 2 pi fct, where t is bounded between 0 and tc. Tc is 1 by fc. And x2t is a sine 2 pi fct from 0 to tc. You know that cosine and sinusoidal signals are orthogonal because they are 90 degree apart. So, but let us compute this. Let us compute this integral and check that. So minus infinity to infinity x1t x2t dt will be, this integral defaults to 0 to tc because the functions are available from 0 to tc. So from 0 to tc it becomes a square cos 2 pi fct sine 2 pi fct dt. So this becomes a square by 2 integral 0 to tc sine 4 pi fct, because it is sine theta cos theta is sine 2 theta by 2. So it becomes a square by 2 cos 4 pi fct by 4 pi fct from 0 to tc, it becomes a 0. So we can say that x1t and x2t are orthogonal because the dot product in the form of this integral, that is equal to 0. Now let us look at these signals. x1t, that is 1 from 0 to 4, x2t is 1 from 0 to 2 and minus 1 from 2 to 4, and x3t is 1 from minus 1 to 0, x4t is 0 to 2, it is 1, x5t is just a negative of x1t. Now, if you look at this x1t and x2t, they are orthogonal because if we take this product and integrate from 0 to 2, it will be 1. From 2 to 4, it will be minus 1. Or it will be 2 from the integral will be 2 from 0 to 2 and minus 2 from 2 to 4. So that will be 0. And if you look at x1t and x3t, they do not overlap at all. So whenever we take the product between x1 and x3, that is 0. So x1 and x3 are orthogonal. x1 and x2 are orthogonal. But if you look at x1 and x4, they are not orthogonal because if I integrate this from 0 to 2, this x1t times x4t from 0 to 2, I will get 2. So that is not 0. So I can say x1t and x4t are not orthogonal. x4t are not orthogonal. x3t and x4t are orthogonal. And x3t and x2t are orthogonal because they do not overlap. Whenever we take the product between the signal, it becomes a 0. And x3t is orthogonal to x1t. x4t is not orthogonal to x2t, nor is orthogonal to x1t. Okay, but x4t and x3t are orthogonal. x5t is actually the negative of x1t, so whatever is applicable to x1t is applicable to x5t as well. So this is how I check the orthogonality of signals. Now when it comes to the orthogonality of discrete signals, I can take the dot product as a summation. Two signals x1 and x1n and x2n are orthogonal if n from minus infinity to infinity is summation x1n x2n equal to 0, then the signals are orthogonal. So this is the way we take the usual dot product. So it is very intuitive. So if I look at the sequences x1n, that is 1 minus 2 3 4 and x2 minus 3 2 1 1. If you take the dot product between that, it will be minus 3 minus 4 plus 3 and plus 4. So the dot product will be 0. Between x1 and x2, the dot product will be 0. But if you look at the sequences x1n, that is 1 minus 2 3 4 and 3 2 1 1, they are not orthogonal, because if I take the product between dot product between x1 and x2, it will not be 0. So they are not orthogonal. Now we come to orthonormal signals. If orthogonal signals have unit energy, the signals are orthonormal. They are just like the unit vectors ax, ay, and az. Okay, they have unit length. Ax, ay, and az have unit length. Just like that, if orthogonal signals have unit energy, the signals are orthonormal. If the signals x1t and x2t are orthogonal, then x1t by root of e1 and x2t by root of e2 are orthonormal, where E1 is the energy of the signal x1t, that is E1 is minus infinity to infinity integral mod x1t whole square dt, and E2 is the energy of x2. E2 is integral minus infinity to infinity mod x2t square dt. If the signals, likewise in the discrete domain, if the signals x1 and x2n are x1n and x2n are orthogonal, then x1n by root of E1 and x2n by root of E2 are orthonormal, where so if the signals x1n and x2n are orthogonal, then x1n by root e1 and x2n by root e2 are orthonormal, where e1 is summation n from minus infinity to infinity mod x1n square, that is the energy of x1n, and e2 the energy of x2, that will be n from minus infinity to infinity mod x2n square. So these orthonormal signals are just like the unit vectors ax, ay, and az in vector algebra. So the summary of understanding, here in this video you understood the orthogonality of continuous time and discrete time signals, then you understood the meaning of orthogonality. But by orthogonal signals, what we understand is this principle is very useful in communication receivers. Okay, if signals are kept orthogonal, it is very easy to, with orthogonals, it is very easy to decompose signals into orthogonal components and detect them. Then you learned about orthonormal signals, and that is the end of this presentation. I thank you all.